Good morning, students. I'll welcome back you to for the next session of the Orifice meter to measure the discharge through a pipe. Here, we shall solve simple problems on Orifice meter. Okay, this is the first problem. An Orifice meter with orifice diameter, right? So orifice diameter, right? DO is given. So I will take this one as DO, right? Orifice diameter is 10 centimeter, will become zero point 0.1 meter. Is inserted in a pipe of 20 centimeter. So pipe diameter is D1. So always remember when it comes to orifice numericals, okay, right? So pipe diameter is taken as 1 always, and O, or you can, some people read this one as not as well. So A naught, D naught, like that. So here orifice, for orifice related data I will suffix as O, and pipe related data I will take this one as 1. Okay, so here for orifice diameter is 10, so it becomes DO is equal to 0.1 meter. Okay, is inserted in a pipe of 20 centimeter diameter. So for pipe it becomes 1. So D1 is equal to 20 centimeter or 0.2 meter. The pressure gauges are fixed in the upstream and downstream of the orifice meter. Gives reading of 19.26 Newton per centimeter square and 9.1 Newton per centimeter square respectively. Then what is upstream and what is downstream? Upstream is, I'll just go back to the diagram that I have drawn during the derivation. Okay, right? So right, so here what is upstream is the fluid that comes into the orifice is all about the upstream, and the fluid that passes the orifice is called as downstream. Okay, right? So more or less most of the numericals are considered like the pipe, or else the P1 is going to be what? P1 is going to be the upstream, right? So section is going as section 1 is taken as upstream and section 2 is taken as downstream. Okay, so in numericals he might give you the same data in different wordings. Okay, so you can say, right, so here P1 is 19.26 Newton per centimeter square and P2 is 9.81 Newton per centimeter square respectively. Coefficient of discharge for the meter is given as 0.6. Find the discharge of water through the pipe. So what is flowing inside the pipe is water. Okay, so the fluid inside the pipe flowing is water, and the coefficient of discharge of the Orifice meter is 0.6. Okay, this is all about the data what he has given, right? So I'll make sure the further calculation takes place. So here diameter D1 is equal to 20 centimeter, it becomes 0.2. So A1 is equal to pi by 4 D1 square, that is cross sectional area at the section 1. So it is pi by 4 into 0.2 square. So it is going to be 0.0314 meter square. Whereas for the orifice diameter is 10 centimeter, it becomes 0.1 meter. So A naught is equal to pi by 4 into DO square is equal to, so I just substitute the value of DO in the uh, 0.1 in the place of DO. So it becomes pi by 4 into 0.1 square. So if I substitute, it will be 0.0078 meter square. Okay, now pressure at the upstream, I have shown it is P1, right? P1 is upstream, so it is 19.26 Newton per centimeter square. But to make it in Newton per meter square, you multiply it by 10 raised to 4. So it becomes 19.26 into 10 raised to 4 Newton per meter square. Okay, similarly for downstream, it will become 9.8 1 into 10 raised to 4 Newton per meter square, and he has given the discharge as 0.6. Okay, now we know this, right? We know to apply this discharge through the Orifice meter. Okay, we know this formula, right? That is Q. Q is equal to CD into A naught A1 into root of 2GH divided by root of A1 square minus A2 square. In the process, I know what is coefficient of discharge, that is 0.6. A naught, AO and A1 values I know. Okay, right? Only value that is unknown is H, right? That is nothing but differential head. So if I could get the value of differential head, I can substitute into the discharge formula and I can simply calculate the value of discharge. So the challenge is to determine what is differential head value, right? So I know this, right? I know this differential head formula. Even in the derivation, I have taken the same expression. So differential head is nothing but P1 by rho g plus Z1 will be minus P2 by rho g plus Z2 is equal to H. This H is nothing but differential head because it is given as horizontal orifice. So datum is going to be in the same height. So Z1 and Z2 will be equal to 0. Okay. In that case, it becomes P1 by rho g minus P2 by rho g is equal to H. This is differential head. So P1 and P2 both values I know. So substitute the values of both. So it becomes 19.26 into 10 raised to 4 divided by 1000. Why it is 1000? Because this is the density of the fluid flowing. So here water is flowing. So it is going to be 1000 into 9.81 minus 9.81 into 10 raised to 4 divided by 1000 into 9.81. So this is going to be, this term value is 19.63 and this term is going to be 10. So the differential head value H is equal to, if you subtract this value, I'll get 9.63 meter. So H is going to be 9.63 meter. Okay. Now the motto of the problem is to determine the discharge through the pipe. So I know discharge through the pipe using the orifice is given by Q is equal to CD A naught A1 into root of 2GH divided by A1 square minus A naught square. Okay, I know what is the value of A naught, that is CD, that is 0.6. A naught is 0.0078 into A1 is 0.0314 into root of 2 into G is 9.81 into 9.63. That just now we have calculated the value of this pressure differential head, right, into root of A1 square minus A2 square. If you substitute, okay, the value is going to be 0.068 meter cube per second, right? So this is how you are going to calculate the value of discharge through the pipe using the orifice meter. What you should remember this kind of problem is how to take the value of H, right? So if you could get the value of H, the substitution is very direct. Okay, so the value of this differential head is calculated by this formula, that is P1 by rho g plus Z1 minus P2 by rho g plus Z2 is equal to H. This is the formula to be used to determine the differential head. And one more thing you should remember is here the water is flowing. Okay, so water is flowing. So there is no here you have to substitute the value of the density of water. So here you have to substitute the fluid flowing density of the fluid flowing. So it is going to be 1000 always for the water. Okay, we shall take one more problem on the orifice. Okay, an orifice meter with 30 centimeter by 15 centimeter. Okay, this is a one more way in which he can give the data, right? Among this, okay, right, when he gives in this multiplication way, means multiplication format, okay, that means the between the two values what he gives, okay, right, the bigger value is always the diameter of the pipe and smaller value is going to be of the orifice. Now what does it mean? An orifice meter with one that I can decode as 30 centimeter is the diameter of the pipe, and 15 centimeter is going to be orifice diameter. The instead of giving long statement, you can give in this short format. You have to remember during the problem solving. Okay, but anyhow, an orifice meter with 30 centimeter by 15 centimeter, the pressure difference measured by using mercury oil differential manometer. Okay, here the differential reading is given, right? Differential pressure difference is measured by using the mercury oil differential manometer. So this H that I will make use, right? I will make use to calculate, no, here, right? But here it is not given directly. Again, there is a indirect way he has given to solve the problem. Okay, right? What he has given now, it is the mercury oil differential manometer reading. He has given that one as X. Always, even in the derivation, I just collect your thoughts here. Even in the derivation, why I assumed this, right? So this is nothing but X, right? This is X. What is X? X is nothing but differential manometer reading. So X is nothing but the difference between the two levels of the mercury. So he has given the differential manometer reading. So he has given the X, right? He has given the X in this particular problem. Okay, right? So I'll just go to that problem. Okay, so here he has given here the mercury oil differential manometer reading on the two sides of the orifice meter is 50 centimeter of the mercury. So I have written differential manometer reading X is equal to 50 centimeter of Hg, means mercury. What he has asked you to calculate, find the rate of oil, right? That is nothing but rate of the discharge of the oil of specific gravity of the oil is given as 0.9 when coefficient of the discharge of the given orifice meter is 0.64. So I have written all the data given in the numerical. So diameter of the pipe, so it is going to be 30 centimeters. So I can write 0.3 meter. So A1 is equal to pi by 4 into D1 square. It is D1 is going to be 0.3. So the A1 is going to be 0.0706 meter square. Similarly, for orifice it is 15 centimeter. If I substitute in the cross sectional area of the orifice, it is pi by 4 into DO square. So it is pi by 4 into 0.15 square. It is 0.0176 meter square. So specific gravity of the oil is given, that is SO, right? I will take this one as SO. Specific gravity of the oil is 0.9, and he has given the differential manometer reading, that is X is equal to 50 centimeter of the mercury. Okay, next coefficient of discharge of the given meter is, that is CD is equal to 0.64. Okay, right? So one thing you should remember during problem solving for the orifice meter is, okay, right, the value what it gives, okay, is X, right? So whenever it gives differential manometer reading, okay, right, it should be in terms of mercury liquid only, right? Mercury liquid, now it sorry, manometer liquid is going to be mercury. So it is going to be in terms of 50 centimeter of Hg. But in the assumptions, okay, this H what you substitute must be in terms of the the fluid that is flowing inside the pipe. Okay, the fluid that is flowing inside the pipe is oil. So what I meant to say is the 50 centimeter of Hg should be converted into some value of the fluid flowing, that is oil. Okay, so for that reason I need to know this formula, right? So that is nothing but differential head formula can be given as this one as well. So H is equal to, that is nothing but for oil, this is generic formula, right? So differential head is H is equal to X into SH by SO minus 1. This we know during the problem solving of Venturi meter, right? What is SH? SH is nothing but specific gravity of the heavy liquid. SO is nothing but specific gravity of the lighter liquid. Among oil and mercury, mercury is heavier and oil is lighter. So that is how I'll just substitute. Okay, so what is X? X is the reading. Okay, reading of the differential manometer. So H is equal to H is equal to 0.05, that is given, that is 50 centimeter, but it is 0.5 meter into the specific gravity of the mercury, it is 13.6 divided by SO. SO is nothing but specific gravity of the oil, that is given already. So it is going to be how much? It is going to be 7.05 meter of oil. See, remember here the X actually in the data was given as 50 centimeter of mercury, but here in the calculation it should be in terms of what? The fluid that is flowing, right? Because oil is flowing inside the pipe, so the substitution of H should be in terms of the fluid that is flowing. That is what you have to remember in the calculation. Okay, so now here H is equal to if you do this calculation, it becomes 7.05 meter of oil. Okay, the meter of mercury will convert it into meter of oil. Is it clear? So by using this differential head formula. Okay, so it is very simple to determine the discharge through the orifice. Q is equal to CD into A naught A1 into root of 2G HO. Why it is HO? Because you have to substitute the head of the liquid inside the pipe. Okay, right, into root of A1 square minus A naught square. So if you substitute all those values, so it becomes 0.64 into 0.0176 into 0.0706 into root of 2G, that is 9.81 into HO, right? Here the oil head is 7.05 into root of 0.0706 square minus 0.176 square. If you substitute, okay, the discharge is going to be 0.137 meter cube per second. Okay, right? This is the formula, right? I have taken this photo, I have taken it from the RK Bansal textbook. Okay, right? Most of the problem that I have solved here are taken from the RK Bansal, okay, Lakshmi publication. Okay, here in most of the problem will be you are going to be thinking, right, what is the formula I should use to calculate the H, right? To calculate the H, okay, sometimes I will make use of this formula. Okay, that is H is equal to all the four formula that are given, okay, are used on the simple or different circumstances. Okay, right, the value of H, that is differential head, is equal to X into SH by SO minus 1. This is used when differential manometer contains heavier liquid, right? Means when water and mercury are connected. Okay, that we have just used in the previous problem. But I can make use of this formula as well. H is equal to X into 1 minus SL by SO. This becomes when the manometer liquid is lighter than the liquid that is flowing inside the pipe. Okay, for example, maybe water is flowing inside the pipe, okay, but the fluid inside the pipe is inside the manometer is, say, some oil of some specific gravity 0.9. In that case, the water is going to be of higher specific gravity and oil is of lower specific gravity. In that case, you have to make use of this formula. Okay, and we have made use this formula as well, no? Right, we have made use of this formula in the first problem. Okay, right? So in the first problem, because specific gravity as well as the manometer differential head manometer reading was not given, so I did not make use of this formula, right? But I made use of this because the pressure difference was given, right? Pressure difference was given in the first formula. Okay, in that case I made use of this one. So H is equal to P1 by rho g plus Z1 minus P2 by rho g plus Z2, right? You just remember this particular formula for the calculation. It makes it very easy. In the first problem that I have solved here, okay, I just collect this. Okay, the first problem I have solved, I have made use of this differential head, right? That is H is equal to P1 by rho g plus Z1 is equal to P2 by rho g plus Z2 is considered because in the data part, okay, he had not given anything with a specific gravity of the liquids. Even in the data, he had not given readings of the manometers. Okay, right? In that case, you have to make use of this formula. But when I take the second problem, okay, right? In the data, he had given what? He had given the reading, right? The reading was given of the manometer, right? So differential manometer reading was given. When he gives the differential manometer reading, okay, right, whenever he gives differential manometer reading, you have to make use of this formula to get the value of H. If he doesn't give the reading of manometer reading, then you have to make use of this formula to determine the H. Okay, once you know the H, it is very simple. Put into the Q formula and substitute and get the values. Okay, I hope you have understood the treats or the very simple logic behind problem solving. The any sort of problem you consider in the Orifice meter, it lies between the calculation of H itself, right? The value of H, once it is found correct, okay, there is nothing inside the in the calculation of Q, right? Q is very simple formula, right? So only that always going to be understood is the way in which the formula that you should use to get the value of H. Okay, let me summarize. If manometer reading manometer reading is not given, then make use of this formula, only this formula, to get the value of H. If manometer reading is given, that is X, okay, then you make use of this formula. Okay, once you make use, you get the value of H, you substitute here, you get the value of Q. Okay, thank you for joining in.